All right, so we are looking at polynomial functions of higher degree. All right, so when we're talking about even and odd, a lot of times we think about, how we categorize things as even, odd, neither. That's not what we're referring to here. What we're referring to here is if your exponent is even or odd, okay? So you can see we've got y is equal to x to the n, where n is even. It's going to have the shape of the parabola. Now, as n gets larger, like if you had x to the 4th or x to the 6th or x to the 8th or x to the 10th, it just has that same shape, but it just gets a little bit wider at the bottom. So you can play around with some of that on your calculator. So if you grab your graphing calculator and go to y equals, you can type in something that is y to an even exponent. And we'll all probably choose different things, and yet the graph that we get will have that same basic shape. So y equals x to the something, where it's an even number, and see what you get. Sure. All right, then try an odd one. All right, where we're talking about, again, not an odd function, but when we're talking about x to the n, where n is an odd number. So, of course, from our toolkit functions, we know this is x cubed, but try like x to the 5th or x to the 7th or x to the 9th. So pick another one, and you'll notice that it has that same shape. So if it has other things that come after it, no, that's going to affect it. But if it is just x to the exponent, then if it's even or odd, it's going to have that same shape. All right, so look at our first example. For the first example, they want us to graph f of x is equal to negative x to the 5th. What does that negative out in front cause? A reflection, yes. Reflection in x or y? X, yes. So basically, all I would have to do is take my normal x to the 5th function. Okay, so again, I know what it's going to look like because it's x to an odd number. And then I'm just going to reflect that in the x-axis. And so here's what that reflected graph would look like. All right, look at the next one. So for the next one, we've got x to the 4th plus 1. So x to the 4th plus 1. Is that going to look like our first graph or our second graph? The first one, right? Because it's even. So what is that plus 1 going to cause? Shift up, yes. So that 1 could be moved to the other side and grouped with the y. So it's a vertical shift of a positive 1, right? All right, then look at the next one. So for the next one, we've got x plus 1 to the 4th. What's that plus 1 going to cause?
It shifts to the left, horizontally.
Yeah, so a horizontal shift of negative 1 or a shift to the left. So again, our goal is to know the base function, the toolkit function, because then we can reflect it and stretch it and shrink it and do all those other things. And we didn't need to plot any points or do anything else. We had everything that we needed there. Okay? All right. So there are some patterns that we can discover when we're working with these polynomial functions. All right, so first off, of course, we know that a linear function has a degree of 1, a quadratic has a degree of 2, cubic has a degree of 3, and quartic has a degree of 4. And it just keeps going from there, like quintic is a degree of 5, and it just keeps on going. But if you think about it, a line doesn't turn at all, right? Straight line doesn't turn. But a parabola turns one time. And we know what x to the 3rd looks like, because that was another one of our toolkit functions. It turns twice. And x to the 4th is going to look like this. It's going to turn 3 times. So what do you notice about the relationship between the degree and the number of turns? It's one less, right? So it's going to turn one less time than its degree. Then there's something called the leading coefficient test. And here's what the leading coefficient test tells me. If my leading coefficient is positive, my graph is going to end going up. If my leading coefficient is negative, my graph is going to end going down. So here's the cool thing about that. Let's say that they tell me to graph x to the fourth and my leading coefficient is positive. All right. If it's positive, I know it's going to end going up and I know it's going to turn 3 times. So I could say, okay, if it's going to end going up and it's going to turn 3 times, that would be 1, 2, 3. I would have a really good idea of what that graph was going to look like before I plotted a single point. Something else that you'll notice is that if the degree is even, like the quadratic and the quartic, they start and stop in the same direction. But if it's odd, like a degree of 1 or a degree of 3, it starts and stops in opposite directions. So again, if we go back to that one we were just talking about a second ago, if we had a positive quartic, the leading coefficient would tell me it ends going up. Because it's even, I would know that it starts and stops in the same direction. So I would know that it starts going up, it stops going up, and it turns 3 times in between. So again, we're trying to find things that will help us to be able to graph without having to plot a bunch of points, right? So again, here's that leading coefficient test that we were just talking about. Your leading coefficient tells you how your graph is going to end. And as we noticed on our chart, that when their degree was even, they started and stopped in the same direction. When their degree was odd, they started and stopped in opposite directions. All right, so look at this first example. F of x is equal to a negative x cubed plus 4x. The plus 4x is really irrelevant. Doesn't have anything to do with what we're looking at. All right, so what's my leading coefficient? Negative. So if my leading coefficient is negative, how is my graph going to stop? Going down. And what's my degree? Even or odd? Odd. So if it's odd, do they start and stop in the same direction or opposite directions? Opposite. So that means that it's going to start going up. Now, another way that they'll express that when they talk about how does it start, another way to express that is by saying as x approaches a negative infinity. Because if you think about it, when we're talking about how our graph starts over here, we're talking about what's this graph doing as it's going off to negative infinity. So how's it start and what's it doing as x approaches a negative infinity mean the same thing. All right, same idea over here. How does it stop is the same thing as how x approaches a positive infinity, because if you'll notice, we're looking at what's it doing as it ends, and that just keeps going and going and going and going. So that's just another way of writing that same thing. All right, look at the next one. So for the next one, we've got positive x to the fourth. So how's this going to stop? Up. My leading coefficient's positive, so it's going to end going up. Since it's even, does it start and stop in the same or opposite directions? Same, so how's it going to start? Up. And then how many times should it turn? 3, because again, the degree is 1 more than the number of turns, right? So it should turn 3 times. So I'm going to start up. I'm going to turn 1, 2, 3 times, and I'm going to stop going up. All right. So I'm going to start up. I'm going to turn 1, 2, 3 times, and I'm going to stop going up. All right, look at the next one. So for the next one, we've got positive x to the fifth. So how's that going to stop? All right, so if the leading coefficient is positive, that tells us how it's going to stop. How's it going to stop? Up. So it's going to stop up. And because it's odd, does it start and stop in the same direction or opposite directions? Opposite. So how's it going to start? Down. And then it should turn how many times? 4. Okay, so I'm going to start down. I'm going to turn 1, 2, 3, 4 times, and I'm going to stop going up. Now, that's what it would do if it was normal, but they're not always normal. If I type this into my calculator, x to the 5th minus x, this green graph is what I get. Well, hang on, it only turned 2 times. I thought it was supposed to turn 4 times. Well, there are some things that can make my graph not turn all those times. Why is the graph having to turn in the first place? What makes it turn?
Why?
Boundaries?
No way.
Ideas? Why does it have to turn? What's it going to do when it turns? It's going back to the x-axis, yeah. So if you think about it, if it has a degree of 5, that usually means it has 5 solutions, right? That usually means it has 5 x-intercepts, right? Because solution and x-intercept are the same thing. Well, what if some of the solutions are imaginary? Are those going to be x-intercepts? No. So for this guy, it's a degree of 5, so we know it has 5 solutions, but it only ended up with 3 x-intercepts because 2 of them are imaginary. Here's another example, all right? Remember in the very beginning today, we started with that idea of x to the 4th, that all of those would have that same basic shape if it was x to the 4th, right? And so this minus 2 right here causes a horizontal shift of positive 2. So we know what that graph is going to look like. It's only going to turn 1 time. And yet it's a degree of 4. And so we would think it would turn 4 times. What makes it turn again? What's it trying to do? Cross the x-axis, right. So look at this guy. For this one, all 4 of its x-intercepts are at the same place, right? So it doesn't have to keep twisting and turning to go hit all 4 of those x-intercepts because they're all right there. So that's why sometimes your graph won't perfectly follow the rules, because maybe you have imaginaries or maybe you have multiple roots at the same spot. Okay, so sometimes it will not turn the number of times that we expect it to for that reason. All right, so I know how to come up with the basic shape. I know which way it starts and which way it stops and how many turns it's going to have and all that kind of stuff. How do I know where to draw it? Like, you know, for this guy back here, like, how did you know to draw that like right there in the center of the graph? I mean, what's to say that it couldn't be like over here somewhere, right? So now that I know its basic shape, here's where I find out where to draw it. So look at example 3. All right, so for example 3, first off, how's this going to stop? How's it going to stop? Up, because our leading coefficient's positive, right? How's it going to start? Down. Why? Because it's odd and they start and stop in opposite directions. If it behaves itself, how many times should it turn? 2. Okay, so I know what this thing looks like. I know it's going to start down, it's going to turn once, it's going to turn twice, and it's going to stop up. Start down, turn once, turn twice, stop up. I just don't know where to draw that. Okay, here's how I know where to draw it. X-intercepts. If I solve this equation, the solutions are my x-intercepts. That'll tell me where to draw this thing. Okay, so if I'm going to solve this, what is the very first thing that you do when you're factoring? Take out what? Greatest common factor. Yeah, so what can we take out? Let's take out an x. And then this quadratic that we have left will factor. So let's go ahead and factor that. And then we can set each of those factors equal to 0. So we'll get x equals 0, x equals 2, and x equals -1. So then let's come over here to our graph and let's plot -1, 0, and 2. So we're going to start down. We're going to turn twice, and we're going to end going up. So the x-intercepts that I have to hit tell me where to draw this. And again, remember that the solutions that you got there, they're the same thing as the zeros of the functions. They're the same thing as the roots of the equation. They're the same thing as the x-intercepts. They're all synonymous terms for the exact same thing. All right. One other thing that I'll mention to you is that when you get into more advanced mathematics, they're going to refer where we've been saying up and down. If something goes up and up and up and up and up and up, it goes to positive infinity, right? If something goes down, 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 it goes to negative infinity. So in more advanced mathematics, instead of saying it's starting up or it's stopping down, then we would say infinity for up and negative infinity for down. So if we go back to each of these problems that we had, you can see for this first example, it would start at infinity and it would stop at negative infinity. Then the next one, it would start at infinity and stop at infinity. It would start at negative infinity and stop at positive infinity. And then this last one that we just did, it would start at negative infinity and stop at positive infinity. So just another way of saying the exact same thing. All right, there are times that they give us something to solve and we just honestly don't have a way to do that. Like we don't have a way to factor it or to break it down. And so in that case, just a reminder that we can use our graphing calculator for that. All right, so we've done this before, but just good review while we're here, that if you want to find the x-intercepts on your calculator, the first thing you're going to do is go to y equals and type in your equation. I usually start with a zoom standard, a zoom 6. That's the 10s all the way around. So here's the graph that we would get. And it looks like I have an x-intercept right here, and right here. So it looks like I'm going to have 3 of them. All right, so let's go find one of them. So I'm going to go try and find this first one that kind of looks like it's around -2. And so again, the way that we did that before was we go to second trace to get to our calculate menu. Second trace. And then we're going to choose option number 2, which is 0. Because remember, solution, 0, x-intercept, root, they're all the same thing, right? So if we're trying to figure out where our x-intercepts are, that's why we're using the 0 of the function. Okay, so I'm going to choose 0. And then it's going to ask me for boundaries, just like it did for maximums and minimums. It's going to ask me for a left boundary, a right boundary, and a guess. All right, so I think my x-intercept is about right here. So I'm going to go a little bit to the left of that and hit enter for the left boundary. And then again, I think it's about right here. So I'm going to go a little bit to the right of that and hit enter to give it a right boundary. And then I'm going to guess. And it will come back and tell me precisely what that x-intercept is. So it kind of looked like -2, but you'll see, yeah, it's not really -2. And I could repeat that same process for the other 2 x-intercepts as well. So if you have something that you're trying to graph, but you don't know where those x-intercepts are and you can't solve it, then just a reminder of how we can get our calculator to help us with that. Now, a couple of minutes ago, we said that if you had multiple roots at the same spot, that your graph wouldn't do all those turns and things that it was doing before. Okay, so what is it going to do? All right, if you have a single root, you're going to go straight through that value. So if you have a single root, you're going to go straight through. If you have a double root, you're going to turn on that point. So think about like y equals x squared. That's one of our toolkit functions, right? It looks like a parabola, right? It turns on 0. So that's an easy way to remember that this would be, if I solved this, I would get x equals 0, x equals 0. I'd get 2 solutions at 0. That's why it turns at 0. So that helps me remember if I have a double root, it's going to turn there. All right, then if you have a triple root, if you think about y equals x cubed, that's another one of our toolkit functions, right? And we know what it looks like. It slides through is what we call it. It doesn't go straight through because then that would be a single root. It's almost like it started to turn, but then it had to turn around and go back up again, okay? So a triple root we call a slide. It's not going to go straight through. It's going to slide through. So that is how our graph will get affected by multiple roots at the same spot. All right, so let's look at this first example here. We've got f of x is equal to x times x plus 2 squared is equal to 0. All right, so to begin with, how's this thing going to stop? What's your leading coefficient? Positive 1, right? So yes, it's going to stop going up. Another way they could say that again is they could say, hey, as x goes to positive infinity, what's your graph doing? And another way to say up is to say positive infinity. So they'll ask it to you multiple ways. It all means the same thing. All right, what is your degree? 3. This was kind of tricky because if you'll notice, there's a degree of 1 on the x, and then there's a degree of 2 outside the parentheses. So if we put the 1 and the 2 together, we have a degree of 3. So its degree is odd, so how should it start? Down, because when it's odd, it's opposite, right? And again, we could say, what's it doing as x goes to negative infinity? And we could say that it goes to negative infinity. All right, so if it's a degree of 3, it should turn 2 times, right? It may not if it's got multiple roots at the same spot. It may affect it, but it should turn 2 times if it doesn't have other factors, all right? So to know where to graph that, again, remember that we solve it. The solutions are the x-intercepts, the zeros, the roots. So I got a solution of 0, -2, and -2. What happens at -2? Is it going to go straight through, turn, or slide? So how many solutions do I have at -2? 2 of them. That's a double root. So what happens at a double root? Straight through, turn, or slide? Turn. So we've already said that we know that this is going to start down and stop up, and it's going to turn 2 times, so I know its basic shape. I also know that it has a repeated x-intercept, a double root at -2, and a single one at 0. All right, so I'm going to start down. I'm going to come up to -2, and I'm going to have a turn there because there's a double root. And then I'm going to go straight through at 0 and end going up. So start down. A double root at -2 makes my graph turn there. And then I'm going to do my second turn to come back up through that last x-intercept so that it ends going up. All right. Next thing that we want to talk about is going the opposite way. Instead of them giving me the equation and asking me to solve it, what if they give me the solutions and they ask me to come up with the equation? All right, so you see how up here we had x is equal to -2, right? Let's go backwards. Right above x equals -2 is x plus 2 is equal to 0. That is its factor form. And the way that we get that is just by setting it equal to 0. So if I have x equals -2 and I want to set that equal to 0, all I do is add 2 to both sides, right? What would the factor form of x equals -1 be? X plus 1. How about x equals 1? X minus 1. And how about x equals 2? X minus 2. All right, so there's their factor forms. Then you'll notice, if we're working backwards on this problem up here, that we wrote it in its factor form and then we strung all the factors together and set them equal to 0. So let's do that down here. Let's string all these factors together and set them equal to 0. So x plus 2, x plus 1, x minus 1, x minus 2, all strung together, set equal to 0. All right, now I can start over here at the left-hand side and just work my way straight across. But you can multiply in any order. 2 times 3 times 4 is the same thing as 2 times 4 times 3, right? So out of these 4, do you see anything that would make this a little bit faster and easier if we multiplied them first?
Just do all the numbers and all the x's.
Okay, x plus 1 and x minus 1, that's a difference of squares, right? If you FOIL that together, you're going to get x squared minus 1. All right, and then, yeah, x plus 2 and x minus 2, if you FOIL that together, you're going to get x squared minus 4. That's a whole lot faster and easier because now all I have to do is a binomial times a binomial. When I started, I had to do a binomial times a binomial, get a trinomial, take that and multiply it times another binomial, get a mess, take that and multiply it times another binomial, get a bigger mess, right? So this is definitely easier. So all we're going to do is FOIL here. All right, so FOIL with me. So x squared times x squared. X to the 4th, x squared times negative 1. Negative x squared. Negative 4 times x squared would give us negative 4x squared. And then negative 4 times negative 1 is going to give us a positive 4. All right. The only other thing that we need is that out in front, we need to know if we have a leading coefficient. The only way that we're going to be able to find that extra piece is if they give us the y-intercept or they give us a point that goes along with this. So if they say create an equation that has solutions of negative 2, negative 1, 1, and 2, then basically any of these would work because you could have any a value out in front and you would still get those solutions. If they say it goes through a specific point, y-intercept or otherwise, there is only one solution that's going to work. And the way we're going to find that is we're going to put 0 in for x and 8 in for y, and then we'll be able to find our a value. All right, so if we put 0 in for x, we know that it's equal to y, it's equal to 8, and so then the only unknown is we can find a. Now, we FOILed this, so if you'd rather work with it in its FOILed form, that's perfectly fine as well. You'll get the same thing. All right, so when we plug in 0, I'm going to get negative 4 times negative 1 is positive 4, so 4a is equal to 8. And then divide both sides by 4, 8. A would be equal to 2. So again, you can leave it in its factored form. You can leave it in its FOILed form, whichever way that they ask for it in WebAssign. So that's how we can create the equation if they give us the solutions. All right, so let's try one more of those and let's put everything together that we've done so far. All right, so we've got 3x to the 4th minus 4x cubed. All right, where am I going to start? Like, I don't even know where to begin with this thing. So where do I begin? Okay, leading coefficient test, how it starts and stops. Okay, so how's it going to stop? Okay, what's your leading coefficient? Positive, so it's going to end going up. All right, so it's going to end going up. How's it going to start if it's a degree of 4? going up because it starts and stops in the same direction. How many times should it turn if it's normal?
4, 3.
So it should turn 3 times unless it has imaginaries or multiple roots at the same spot that might affect that. All right, so if I start up and I turn 1, 2, 3 times and n going up, it's going to have that W shape, right? Okay, how do I know where to draw the W? X-intercepts, all right? So let's go find our zeros, our x-intercepts, our roots, our solutions, all right? So let's take this equation right here. Very first step is to always factor. So what could we take out as a greatest common factor? X cubed. And then we're going to set each one of those factors equal to 0. So I'm going to get x cubed is equal to 0. Take the cube root of both sides, and basically I'm going to get x equals 0 3 times, right? Like x cubed literally means x times x times x. So that is a triple root at 0. What happens at a triple root? Straight through, turn, or slide? Slide, yes. All right, so let's see if we can draw that W shape with a slide at 0. And then for 3x minus 4, if we set that equal to 0, we're going to have a single root at 4/3. So we're going to go straight through at 4/3. All right, so go ahead and sketch what you think that's going to look like. It's pencil. You can erase it. Just sketch what you think it might look like. All right, so let's see what we got. We said it was going to slide through at 0. We said it was going to go straight through at 4/3. We said it was going to start up and it was going to end going up. So really the only thing that I don't know is I don't know how steep to make this over here. And I don't know how low down to come down here. So the way that I can figure out how steep to make this up here and how far low to come down here is just plot a couple points. So I'm going to plot -1 to figure out what's going on the left, and I'm going to plot +1 to figure out what's going on the right. Okay, so if I plug in -1, I get 7. That thing is pretty steep. And if I plug in +1, I get -1. That's really shallow. I thought it went down a whole lot further than that. So we graphed that with 2 points. Otherwise, to graph something that accurately, it would have taken a bunch of points. And look, that majority of that graph is in between -1 and +2. So that means if I'm plotting 10 points, most of them are fractions or decimals. That's so much fun, right? Because I want to take a fraction or a decimal and raise it to the 4th power and raise it to the 3rd power and then combine it and get a common denominator. And ugh. So again, this just gives us tools that we can use to help us with our graphing. Okay. So the last thing that we want to talk about is something called the intermediate value theorem. The intermediate value theorem is actually something that we use in calculus in lots of different applications. The short version of the intermediate value theorem says this, that if you have the point AF of A and BF of B, they're 2 points on the graph of a polynomial function, just as long as they're not equal to each other, then for any number D that's in between the two y values, there must be a number c that's in between the two x values so that f of c is equal to d. Here's what they're saying. If you have a y value in between these two y values, it has to have an x value that goes with it. You can't have a y without an x. So there'd have to be an x value that goes with it that is between those two values. All right? So that's the intermediate value theorem, and we can apply it into a lot of different settings. So if we go back to that same problem we were just using, 3x to the fourth minus 4x cubed, and it says, is there a root between 1 and 2? Well, I can look up here at my graph and see, yeah, there's a root between 1 and 2. Well, what if I hadn't graphed it? I can use the intermediate value theorem to help me figure it out. So first off, I need to know what my ordered pairs are, because this whole intermediate value theorem talked about 2x's and 2y's, right? All I have right now is 2x's, 1 and 2. So let's go ahead and plug 1 into the function. When I plug 1 into the function, I get 3 minus 4, or negative 1. And when I plug 2 into the function, I get 16. Now, if you're going from 1, negative 1 to 2, 16, are you going to have a root? Yeah. If you're switching from a positive to a negative or a negative to a positive, you got to go through 0 to do that, right? And so that's how the intermediate value theorem helps us, because it says, look, I know that I have these two y values, negative 1 and 16, and there's got to be a 0 in between them, because you can't change signs without a 0 in between. So if there's a 0 in between them, then there's got to be an x-intercept, because anytime y is equal to 0, you have an x-intercept. And the intermediate value theorem said, if you have a y, you got to have an x. All right, let's make this simple. If they ask me, is there a root between 1 and 2? They're basically asking me, is there a sign change? If there's a sign change, so like negative 1 to positive 16, yep, then there is going to be a root. If there's not a sign change, then there's not going to be a root. Okay? So now that we kind of understand what the intermediate value theorem is and the reasoning behind it, we want to be practical. When we see a problem like this and they say, is there a root between them? It is the exact same thing as if they said, is there a sign change? If there's a sign change, then yes, there's a root. If there's not a sign change, then no, there's not a root.